Hello, everyone. Welcome to the second episode of Digitalisation of Utilities. I am your host, Ninad Jagtap. The topic for this episode is the balancing transformation for the future electricity system operator. In this episode, we will discuss how electricity balancing system or solutions are transforming to accommodate changes in electricity market. Hello, Christoph.
Hi, Ninad. Very pleased to be with you today.
Thank you. Christoph is an associate partner for global energy, environment, and utilities at IBM. He has led various strategic engagements and complex programs for utilities. So today's topic, which is balancing transformation program, is a complex topic to discuss because balancing program sits at the heart of the electricity industry, and especially with the system operator. So Christoph, let's start with a basic question. What is the role of system operator in electricity market, and why are we talking about this balancing transformation program? What is the importance of it?
Yes, so indeed, the system operators are playing an absolutely key role in the overall energy system. Basically, their role is to balance the energy that is being injected in the system with the energy that is being withdrawn. And typically, they have to do it in certain geographical areas, network areas, at typically national levels. Mm-hmm. But there's a few countries in Europe where you will see several system operators. Generally, it's one per country. And this one is very complex because, as everybody would probably know, it's difficult to store electricity in large quantities, which means that at every given moment, the power that is being injected needs to be balanced equal to the power being withdrawn. So, and as you know, we in Europe and now almost everywhere in the world, the power markets are competitive markets, lots of players. So at some point in time, it needs to be synchronized because basically you will have power sellers and buyers who will exchange this power ahead of time when the actual power will be delivered, right? So you have the long-term, let's say, planning, which we call the forward markets, and then you have the power exchange market, where people basically injecting or withdrawing, so selling or buying, will commit to certain quantities, right? And of course, it has to converge with an equilibrium. But typically, at some point in time, before the power is actually being, injected or withdrawn, 1 hour before, there is some variation across the world, but a few minutes before, the system is being taken over by a single player that will orchestrate the overall, let's say, transactions, but also the delivery of the physical goods, right? So, and this is the role of the system operator to be this single orchestrator of the physical delivery of the power, yeah? And typically, if the power is very much in balance, that's great. They don't have, let's say, much to do, but most of the time, it's not completely in balance, which means additional power needs to be injected or withdrawn, yeah? Stop me, I'm being too long, but that's important to understand all what are the key, let's say, use case and activities. So it's really about, so they are the sole authorized party that can actually at this given point in time buy energy, more energy if needed, or ensure there is more load on the system, so that the balance is achieved. But before that, they also need to do some kind of planning to ensure the network, the overall energy system, remain in a state of operability is the term. It means that some of the parameters of, let's say, the power quality, and a very important parameter is called the inertia, which is the sensitivity of the grid, if you wish, to imbalances. It needs to ensure that inertia is good. Otherwise, the grid will become way too difficult to balance. So it's just to give you an idea, right? So they are the orchestrator of the physical delivery of the goods.
Yeah, and they are the one who creates this wholesale market, the operator of a wholesale market, in short.
Yes, well, they certainly operate, as I said, what we call the gate closure. So a few minutes before the real time and the power is supposed to be delivered or is drawn, they are taking over the power market. Yeah.
Okay. And especially when
And by the
we
way,
talk.
they dispatch also in certain countries, they're also responsible for dispatching to the different generation units the quantity of energy that they have to deliver.
Okay, so let's go back to the second
Question
question
two.
that we have, right? What is the base purpose of this balancing program if you consider the future energy markets and especially
Yeah.
considering the role of renewables in the electricity market?
Yes. So traditionally, the energy system, the power markets, was served by a limited number of very powerful generating units. Yeah. So it could be gas, nuclear, or coal. There would be 50 megawatt of power and capacity and above. So the number, it was a game that was played by a fairly limited number of units. So it's a bit like, a small orchestra to orchestrate, if you wish. But as you know, we are currently decarbonizing power market. And so those big units are gradually being replaced by a large number of smaller units, renewables
Yes.
mostly, we call distributed energy resources. And we call them distributed like wind farm and solar farms and the rest. I call them distributed because they are no longer connected to the transmission system. They are actually connected to the distribution system. So there's many of them and very, very distributed across the territories and the networks. And that fundamentally changes the way energy system has to be managed. Today, if we look at the balancing system, it's really designed to synchronize a limited number or large units. So now we will have to accommodate a very large number, thousands and thousands and thousands of units. So it's a completely different scale. So this is the number one challenge. So they have to be able in the future to dispatch much smaller units, typically even less than 1 megawatt, right? So it could be, 500 kilowatts or on and even lower. This is one. The second is because those units are not connected to the transmission network as the big units we are operating today. The transmission operator, sorry, have limited visibility on those units, and so the system operator has limited visibility. So they need to get much better visibility on how those units, DERs, are operating. So this is the area what we call situational awareness, a much better understanding and a much wider understanding of the overall energy system that will include the transmission system, but also the transmission network and distribution networks. So that's the second challenge. And there is the third one. There's a whole bunch of new issues. I mentioned inertia quickly previously. Inertia will have to be managed quite differently because the traditional units, the big ones, were also providing lots of inertia to the system. Meaning the frequency, right, that it needs to regulate, it could be 50 or 60 years, depending where you are in the world, will not be too sensitive to imbalances. But with those units getting off grid, renewables do not provide by initial design, I would say, the same level of inertia. So the network becomes much more volatile. And the final thing is because, renewable power or intermittent power, there will be some imbalances coming from the fact that forecasting will never be perfect. So if you combine all those elements together, there's some new functionality required to address inertia differently. And a few other, I would say, power quality parameters that will have to be managed fundamentally differently.
Yeah, so a lot of energy that's to get generated. So if we consider the traditional electricity market with large number of electrical provider, it was much more easier for system operator to balance the demand and supply of electricity. Now, because of these smaller renewable sources, there are more challenges coming up, and especially because they are distributed and not necessarily connected to the transmission network, it's creating more problem for the system operator to balance the demand and supply. Now, what sort of solutions or systems were used by the system operator to balance this demand and supply?
Well,
and what would be changing in terms of balancing transformation program?
Yeah, so they were typically fairly, monolithic systems designed in the year 2000. or even before. We still have some application that were developed with Fortran, very old, now quite old language. So typically the generation of the systems were the year 20s or even the 90s in some areas in Europe, when typically developed when the market were made, power market were made competitive in Europe. So it's quite a few decades ago. And of course, the system has been expanded, modernized to some extent, but not allowing to accommodate, as I was saying, such a high volume of market players. And beyond market players, system operators is basically, they are buying services also from a number of, let's say, service providers to help them balance the grid or address some of the power quality parameters like inertia. There is a few others I won't mention. And so they also need to expand, let's say, the catalog of service that they will need to procure, to address these power quality challenges. And they need to do so in such a way that they really provide a level playing field so that all types of service providers have a fair chance, right? And so this is really creating a completely different market, much diverse, much more players, much more types of services, and again, a much higher quantity, volume of players in the overall game, I would say. And that really calls for a complete redesign of the systems. We also know that the journey to net zero is by no means finished, right? So the systems will have to evolve, as we are progressing in our net zero journey. And so a new level, I would say, of system flexibility is also required. One of the problems also system operators have with their legacy system is that they are very complex, so very, very slow to adapt. So each time you have a new regulation, as the market are maturing towards net zero, right? It's a very long and cumbersome process to adapt those systems. So the flexibility is also a key element that the new system needs to bring.
Okay, so it starts with first onboarding these new energy sources on the legacy system, and then how legacy system adapts to these changes, and how we start building the way we balance the electricity or
So the main, let's say, the functional blocks, right, is to interact, let's say, select what are all the service providers that can participate and provide some services, right, that the system operator will require to activate in certain conditions. Typically, system operators are also redesigning what we call their market-facing platforms and service procurement platforms. That's not really core or part directly to balancing, but that's the first step. You need to select and procure and qualify and validate, right, different units that will provide some service at some point. The second stage really is about understanding, and that needs to be done for every 30-minute slot, right? It's a real time, day and night, 365, 24 days. Conditions in which the network will operate, and you have a large variety of situation. It could be high demand with low wind, which means that the big units will be back, or it could be low demand, high wind, and high renewables, so much more unstable and volatile situations. And so they need to understand what they will need in terms of services to operate the network reliably. And that's something that is being done a few days before, based on some, forecast. And so the second stage. So we sort of call it secure the network. So what is needed to operate the network in a secure manner? And then when we have an idea what was going to be required, it's about procuring it in the most cost-effective way. All right, cost-efficient way. So these markets, these services are provided in a competitive manner. There are some auctions being organized beforehand. And so the balancing system needs to select the players that would have put the best bid, right? What we call the best merit. to provide the services according to the requirements designed previously. And when this optimization has been done, right, really to reduce the cost of the services needed to operate the network, it could be energy, but a different type of services as well. And it's about instructing the set of instruction that needs to be sent to all those units and service providers. Yeah. And so that's the next stage. And then at some point in time, when the time has come and we're getting absolutely close to real time, then those instructions are going to be sent to the different units. It's about monitoring that this instruction has been received properly and executed properly, and manage any kind of imbalance or remaining imbalance if anything would go wrong in this chain, which is a real-time chain. Yeah. So there's all aspect of monitoring that the instructions that were designed are properly executed, and if not, to activate some form of contingencies plan.
Okay. So what sort of role that you play and what sort of consulting approach do you take for such complex balancing programs?
In this case, the role of IBM is primarily the role of a technology partner. For me, it's probably one of the largest, let's say, legacy system modernization in this industry globally. Our role was initially to act as a architecture, let's say, design authority role, helping shape how the new system should look like to deliver on the functional requirement, but also the non-functional requirement that are very demanding, by the way. And also help them, because they are complex systems that takes a long while to develop. So it was absolutely mandatory to execute with an agile format and incremental delivery. So we help also provide this agile at scale capabilities for complex engineering, complex system. And so that's the main role of IBM. And of course, that was for the design part. And now we're also providing a number of capabilities and development. The choice was made to, of course, implement state-of-the-art, let's say, cloud-native software engineering approach. So modular architecture, microservices, DevOps, completely DevOps enabled. So that's the role of IBM. It was to really provide the design authority, architectural support, but also now the development capabilities and testing capabilities. And there was another one next to that in parallel, is to help also, let's say, in the business work streams, which was about ensuring the benefits will be realized. That's that stream I'm leading. That includes really deploying a kind of benefit realization framework and benefit tracking and change management, because the change in the control room will be quite significant. So for control room engineers, and that there is lots of constraints. Again, it's a 24/7 activity. So fairly complex rosters, et cetera, et cetera. So it's a complex environment where to drive change. And so that's also a responsibility to help our clients to execute according to the best practice and ensure there will be zero disruption. And we have something like 8 major releases over time. So it's going to be a very significant journey, right? So we need to get a well-designed, repeatable, effective approach to overall release, deployment, and change management.
So when you were discussing about the requirements, what was your method to, defining the scope for this program and how?
Yeah. So it was a combination of reverse engineering the existing system. So the business is not fundamentally changing. What is changing is we need a completely different scale. We need much more flexibility to introduce new type of services to be procured, right? To address the new power quality challenges, right, and network operability challenges. Fundamentally, the basic processes will remain the same. So a big source of information was reverse engineering of some of the system. There are several of them that are currently supporting the control room. But there were some new capabilities to be also injected. So how to bring this flexibility? So for example, most logic of a service will not be hard-coded, but the idea is to use rules engine, for example. Use a kind of a meta service definition that will be used as a straw man, if you wish, or an archetype to create new services without having to change, to enter in kind of a low code type, right, environment. So these are more structural changes rather than fundamental change of the processes. So a lot of the, let's say, user stories and features for epics, were elaborated, of course, in collaboration with the existing teams active in the control room, but also fed by reverse engineering of the existing system.
Yeah, and especially talking about the control room, right? And these control rooms are very strictly monitored, and aging is a major challenge that control rooms are facing.
You get it. Absolutely.
But then, considering that these systems are 10, 20, 30 years old, right? Adding these new features, making sure that your customers in the control room are happy with these new changes and accepting these new changes. How difficult was it to get the required communication with them and getting their acceptance on different ways of working, right? Because of this.
Yeah. So they are heavily involved, of course. And the second is there's one module in the program, one work stream, if you wish, which is completely dedicated to the, let's say, the user interface, extended vision for what we call here in this case, we call the common display, which is to rethink completely how information is being displayed to the end user. So the overall, really, the end user experience for the system. And there is a lot of mock-ups being done. There's been a lot of thinking that was injected in there, and trial and error as well, to ensure that we're building a new interface that really allows to consume a large volume of information, which is actually one of the challenge, of course, as you know, in a control room with zillions of screens everywhere, but ensuring that we are reducing this by having a very efficient, effective way to provide this information, but flexible as well, so that the end user can configure the screens and really get exactly what they need. So there is a lot of efforts being dedicated to that space. And frankly, it looks really great. And that creates also a kind of platform that, will receive, probably more and more information in the future, but in a way that keep it easy to consume. Yeah.
Yeah, because if you see the screens that appear in front of in a control room, there are hundreds of screens that they are watching, and it's very difficult to pinpoint, isn't it?
It is, and frankly, there is also data duplications. Each issue is managed in a separate screen because it's probably a separate application behind it. The idea is to really build a single interface that will be fed by all the different, let's say, data streams. And display in a completely user-centric way. It's very stressful the way it is actually, because it's easy to make a mistake. On top of that, there is a whole number of, let's say, additional applications that were developed actually by the control room people themselves and bolt on the let's say, the main platforms, which create another layer of complexity, of course. So we reviewed all those apps to also take all those sometimes great ideas that was embedded in these apps and inject that back into this common display, common user interface or common user experience layer, if you wish.
That must be very complex. I imagine that, and especially.
Yeah, no, I was amazed by the capability of IBM in this space. I mean, there was a combination of design people and developers and many different mock-ups. We have fantastic capabilities in this space.
And what about the training? Now, once we start changing these systems, and there must be some training programs. Is there?
Yeah. So we're currently designing this actually. So the idea, it's a very good point. So there is a lot of training that were taking place, a bit of classroom. And let's say, you are becoming, or you aim to become, to authorized to operate in the control room, right? On the given role. There are several roles, but I don't think we have the time to discuss all this. But whatever the roles, you will follow a bit of classroom training, and then you will be sort of trained on the job with, of course, heavy supervision. So you will have the supervisors working with you, and it would take, something like 6 months. So it's a very, slow process. The idea would be to do it differently. First, much more e-learning, Yeah. And the idea is to provide a complete simulation system that will be, of course, a kind of a copy of the real life system, so that we could train a kind of a flight simulator
Okay.
for control room engineers. So there is a whole plan to implement that new platforms and train the control room engineers on the simulator, so that we could speed up the training cycle and really increase the quality of the training. So again, that's going to be rolled out gradually, and that's let's say the major change, right, in the way training is going to be done. And so that's the direction for the next years.
Okay. And I understand this is very complex system to even talk about, and especially complex market that we are discussing. And
Yeah, absolutely.
okay, so
It was sufficiently clear.
yeah, Christoph, it was a real pleasure to have you as a guest and to give some insights on this balancing program. And thank you for your time.
It was a pleasure.
And let's definitely have another session to discuss some program progresses.
Absolutely. There will be some lessons to take, for sure.
Thank you.
Thank you, Ninad. Bye.
Thank you. Bye.